In this video, we look at one of the key ways of finding the derivative known as the chain rule. Enjoy. Cool, let's begin. So, this class is going to cover, it's a fairly brief and quick chapter, this one here. Essentially, all we're going to be looking at is the chain rule here. Now, it's going to be pretty brief because, well, the chain rule is a very quick and easy thing to do. Essentially, what we've looked at beforehand was how to handle the basic derivatives of the simpler functions. So if there's nothing super complicated involved, then under those circumstances, finding the derivative is literally just a matter of looking at the table of derivatives. So this table of derivatives, you'd be able to just sort of look and clearly see your function is one of these things, and so you can very quickly find the derivative afterwards. The chain rule is what you use when you get anything other than what you're seeing here exactly. So if this said like e to the 2x, for example, if this said like 3x plus 4 to the power of n, any slight variance on these functions is when you start using the chain rule. The chain rule is a product of two derivatives. Essentially, what you have to do is define an inner function and an outer function. The easiest comparison I can give is when you have a composite function. So when you have a dedicated function within another function that is a composite function, this is where you would use the chain rule to sort of solve that, that type of equation. One example that the book gives here is you have something raised to some power. That something in this case is a cubic, and that power is -2. The similarity here is that this takes the form of our first equation for the derivative, this x to the power of n. You have something to some power. That something is a cubic, and that power is -2. So that derivative applies. The question then becomes, how do I actually do that? Well, what you do is you start by defining whatever the inner function is, in this case the cubic. You define that as its own separate thing. The book will typically use u as the definition there. From there, you can rewrite your y equation purely in terms of u. So instead of saying y equals 4x cubed minus 5x all to the power of -2, you replace this bit with u, and then that's just going to be y equals u to the power of -2. That gives you two unique functions. The way the chain rule works is that you want to find a derivative of each of these individually and then multiply them together. So we have u is that cubic. The derivative of u is therefore going to be the same way you treat power law functions. Power of 3 goes down the front to make 12, reduced by 1 to make x squared, and then -5x is just going to become -5. That's that bit there. And then derivative of our bottom one, you're deriving with respect to that new variable u. So that power goes down the front, -2, and it decreases by 1, so down to -3. All you do from here is multiply these two things together. So you're going to have your -2u to the power of -3 multiplied by the 12x squared minus 5. From there, you want to get everything back in terms of x. And so they've kind of done all the simplification in one single line. What you would do is plug whatever u was, so you'd plug this cubic back into this spot and then expand everything out from there. That's really it. You've defined whatever's on the inner as its own separate function. You rewrite that function with that simplified version, find the derivatives of each of these terms, and then multiply the derivatives together. Now I have that's the wrong page, sorry. I have a framework that you can follow if you like using these notes. It's just those few steps. I've used G instead of U, but the letter doesn't actually matter. And at the very bottom of this document that you'll find in the classroom, there will be an appendix on how to handle literally every single possible combination. So one here is what happens if you have a polynomial to a power? What happens if I have a circular function to a power? What happens if I have a tan in a log? What happens if I have a log in a sine? You'll see all of them worked out, and you'll at least have that to reference. Fundamentally, that's all we're doing though. What is on the inner gets defined, derivatives of each, and then multiply together. Now, as far as applications of that, it's the same as applications for any other derivative. You might be finding the gradient of a tangent line, in which case you are, when you find your derivative, that is your gradient function. So to find the gradient of the tangent, you would then just sub in that point, specifically the x value, afterwards to get the gradient at that spot. So in this case here, one thing you could treat this one like is a hyperbola. You've got some constant divided by something with x in it. That doesn't normally look like a hyperbola until you define the entire denominator as u. So if you replace the whole denominator with u, you'd have 16 divided by u, or as written here, you have 16 u to the power of negative 1. Find derivatives of each. So this one becomes 6x, this one becomes negative 16 u to the power of negative 2. You take these two things, multiply them together. Just be sure to replace the u with the 3x squared plus 1. That's going to give you your derivative down here. To find the gradient at a specific point, you then just sub in that x point. Those are the given examples there as far as chain rule goes. Anything to clarify there before we get into some questions? Okay. So we're going to go through a few of these live now, just so we can test our understanding. One thing that I'll do to help out here is, because a lot of this will be coming from your understanding of the derivative table, you need to be able to figure out what function is what you're looking at most like. So does it look most like a power function? Does it look most like a circular function? What does it look most like? So what I'll do is I'll do a screenshot of that in the chat so you can reference that if you need to. And from there we'll just sort of work out of the book. I'll write those down on the handwritten notes. Okay, so the first one we'll have a look at is going to have y is equal to x squared plus 1 all to the power of 4. So the first question I would have is, this function, what is it most like on the table of derivatives?
Polynomial?
Yeah, polynomial, absolutely. So that means that when we do our substitution, we want to do a substitution that makes it look like that x to the power of n. So what should our substitution be to make that look like the way we want it?
Would we first define x squared plus 1 to like be a one single variable? Like,
Yeah.
or u?
Absolutely, yeah. That's step one. So this definition here, once you replace that with u, you'll have y is equal to u to the power of 4. And from there you can see that it looks like one of our table of derivatives, things we could easily solve. That's just some x to the power of n, or in this case, u to the power of 4. Cool. So we have our definition and we've rewritten our function to accommodate. How do we therefore complete the chain rule for the derivative here? So there's the chain rule all written out. This is what we want. To get it, we need to figure out these things. So that's what we want. We currently don't have either of these. What might we do to get them?
Do we follow the rule nx to the power of n minus 1?
Yeah, for both of these, that'll be applicable. So if I wanted to get the du on dx, so derivative of that, what would that end up being?
Do we use 4u to the power of 3?
Oh yeah, sure. So if you wanted to do that one instead to start with, you'd have dy on du is equal to 4u power of 3. Yep. So that's that one checked. We have dy on du. That's that. Still need this one. What's that going to be?
Will it just be 1 because we do x squared plus 1 to the power of 0?
Squared plus 1 to the power of 0. So this is still the power function thing. You got x squared. So the same way that you handled it here, where you had u to the power of 4, you brought the 4 down and made it 3 as a power. Same thing you do here. X to the power of 2 means the 2 comes out the front, and the power becomes 1. So you're going to have your du on dx, derivative of this. So that 2, as I said, is going to come out the front. X is going to be power of 1, and any constant value always disappears when you do the derivative. Don't need to re-explain why that is the case, so we're happy enough with constants disappearing on derivative. Okay, we've now got each of our two terms. The chain rule says we should multiply those things together, and so that's what we'll do. So our final thing, dy on dx, that we're trying to find is the product of 2x and 4u to the 3. Now, we don't want to have multiple variables in there. We want everything to be the same variable. So all we're going to do is replace that u with the equivalent x. So u was x squared plus 1. So when we do our derivative, dy on dx is equal to, well, 8x first, combining those two. And then the u is the x squared plus 1, all cubed. And that'll be it. You can either fully factorize or fully expand. Those are the rules. This is fully factorized. Wouldn't really recommend expanding that. Not pleasant. But yeah, that's the gist of how that works. Derivative of inner, derivative of outer, multiply the two together. All right. Do we want to practice any more of those from question 1? Because those are all pretty much the same thing. You got unique versions where they've got like other letters in there instead of numbers. Yeah, we'll at least look at that one. And there's also like negative indexes as well. Yeah, okay. I'll do D, but keep in the back of your mind if there's any more from question 1 you want me to have a look at. Okay, so D is ax plus b all to the power of n. That's our function. Reminder, derivative is going to be dy on dx is equal to du dx multiplied by dy du. All right, so this is fully alphabetical now. How do we handle it when it's like in this case? It is the same approach, I'll mention that much, but the actual like doingness of it will look different. So the first question to ask is, what does this look most like on the table of derivatives? What's it closest to?
The quadratic one?
Yeah, the quadratic one, x to the power of n. So, what sort of substitution would we have to do to make it look exactly like an x to the power of n type situation?
Let u be ax plus b.
There we go. See, look at that. Exact same idea. Take whatever's in the brackets, u equals ax plus b, and then rewrite our y purely in terms of u. It's a bit of a weird one, u to the power of n. Cool. Those are our two functions, and those are going to correspond to these two derivatives here. So we need to derive both of these functions. The question now becomes, how do we handle that when there's no actual numbers in there? Once again, it is the same approach, but it's going to look a little bit different to what you're used to. Maybe first up, how do we find derivative of this one? What might that look like? Very talkative today, aren't we? So this one here essentially is a kind of power function. Whenever you have ax, even if the power isn't necessarily like explicitly written, that is still a power of 1. So it is still something raised to a power, which means we still treat it like we would for any power function. So yeah, PR, the derivative will be a. Nice. So the way that works for everyone else, you're going to have du on dx. This is the same as saying ax to the power of 1. So that 1 is going to come out the front here. 1 times a is a. That 1 is going to go down to 0. And anything to the power of 0 is 1. Once again, a times 1 is 1. That's why we're only going to have that a out the front. Then this b over here, we treat that as a constant. And the derivative of any constant is always going to be 0, which is why this derivative is just going to be a. As for this one, dy on du, what might we do there? We've kind of had a look at how this works beforehand, but we haven't looked at what happens if the power is unknown. What might that look like? This one you could almost rip entirely off the table, as printed almost.
Do we bring the power down and then subtract 1 off the original power?
Absolutely. N times u to the power of n minus 1. So even though you can't know what n minus 1 is, you can still write exactly that. And that's exactly how it's written in the table. If you have x to a power, then that power goes down the front and is reduced by 1. The only difference between what I've written in the pre-written notes and what I've written here is the u instead of x. It's the exact same. Okay, finish off the chain rule. So we have each of the terms we want. What's our final answer for derivative that we're looking for?
Or ax plus b cubed.
Yx plus b cubed. Yeah, let me just double check what I had for u. It's going to have a bracket, well, an bracket ax plus b n minus 1. Not too sure where the cube came from. We may be looking at a previous question, I wonder. But for the most part, it's just going to be the product of these two things here. You got a, you got n to the power, n times u to the power of n minus 1, and that's going to give you the a times the n at the front here. This is u, it's the ax plus b, and this is the n minus 1 there. That's about it, really. So again, in order, do your substitution, rewrite both of your... Yeah, no worries. That's my handwriting issue for reading n as 4. Okay, yeah, so derivative of each of those individually, then multiply through together, and you're sorted. Cool. That's about it for questions 1 through 2. Unless there's anything else in there you want me to have a look at, let me know. Otherwise, those should all be the same. Would then move on to question 3, which is now an application of that. So I'll start writing that one out. In the meantime, let me know if there's any other question you want to do. Y equals 16 over 3x cubed plus x, and point is 1, 4. And we want gradient of tangent. So we kind of looked at a question very similar to this beforehand. Anyone remember what step 1 would be for finding gradient of a tangent line?
Would we be converting to a hyperbola by substituting something for the denominator?
Yeah, precisely right. U is equal to 3x cubed plus x. Therefore, y is going to be, you can write 16 over u, but when you actually go to do the derivative, it's probably a bit nicer for you to write it with a negative index. That's just a personal preference thing, though. It tends to be easier to do a match on the table. Yeah, then from there, we just, once again, continue the same way we've always continued chain rule. What should be the next two derivatives?
Should one of them be negative 16 u to the power of negative 2?
Yep. dy on du, negative 16 u to the power of negative 2. Yep. So that's from there to there. We also want this one as well. What are we doing there?
Is it just 9x?
9x squared plus... Yeah, this one should have been 9x squared plus 1. So you've got this power of 3, which comes at the front. So that's good. You've done that one, which is... So du1 dx is equal to 9x. The next part is this power has to go down by 1. So instead of having power of 3, we're going to have power of 2. There is also this second term in here, this x. The derivative of that is also a sort of power function thing. This is the same as x to the power of 1. So 1 comes out the front and becomes 0. So you've got this 1, and then x to the power of 0 is also 1. 1 times 1 is 1. So final derivative there is going to be 9x squared plus 1. Then from here, yeah, how might we finish this one out? At least as far as derivative goes.
Would you want to convert the u back to its original form so it's easier to multiply?
Yeah.
Or
Yep.
Yes.
For sure. dy on du is going to be equal to negative 16. U was 3x cubed plus x. So slapping a negative 2 on there. Cool. Yeah, I got that. What do we do now that we have those?
And we distribute the negative 16 to 9x squared plus 1.
Yeah. So it's going to be a product of these two terms. So you're going to have, would you distribute it? So one of the things you'll run into if you try to distribute this is you're going down a path of fully expanding rather than fully factorizing. So the recommendation would be to just sort of leave it out as factors. So I'd have like the negative 16 out the front from here, the 9x squared plus 1 out here, and then you could have it as a negative index if you like, but we will be using this term anyway, so it might be worth rewriting it as a positive index. So 3x cubed plus x on the bottom, and then just leaving it like that is fine as a derivative. The negative index also is fine to have, but I'm only writing it this way because we'll be needing it shortly. Okay, so that's our derivative. Does anyone remember what the derivative actually tells you about a function?
The gradient at like a given point.
Yeah, the gradient for any given point. So if we want to find the gradient of the tangent to this curve at a given point, I'll rewrite the point down here. The point was 1, 4. What are we going to do to actually achieve that?
We need to look at the tables of like differentiation, like what function becomes after like division.
So we this is actually already our derivative function here. We don't need to rederive this one again. So all the effort that we put into doing derivative, that got us to here. P is more on the ball with this one, which is just sub in the x value from the point here. Because as you said before, derivative does tell you gradient for any value of x. Here's the value of x we care about. And so all we're going to do is replace every x in here with the 1, and then we'll be sorted. So you can kind of see why plugging in x equals 1 into this might not be so pleasant. Oh, I just realized I didn't even put the square on this thing. Jeez. Yeah. Power of negative 2 should have made a square here. But okay, so our gradient, I'm just going to call it m, negative 16 bracket 9 times 1 squared plus 1 all over bracket 3 times 1 cubed plus 1 all squared. This is just pure arithmetic at this point. Minus 16, 9 and 1 is 10, 3 and 1 is 4, and then square that. 4 4s are 16, and the 16s will cancel, giving you just negative 10 there. Was any of that approach unclear as to how we get our final answer of gradient equals negative 10? If so, let me know, either by hopping off mute or by text. In the meantime, I will look and find a new thing to do. That's misplaced. Huh. Is that question 5 even doable with our information? Hang on just a moment. F dash is that. No, that's anti-diff. We can't do that. Have we? Maybe they're just assuming that we already have anti-diff information. Here's unit 3-4. Anyway, that's really about it for the... Oh, actually, there is an interesting one down here in question 8. Let's have a look at that. because you may not have to, or you may not know the actual functions that you're working with. You may have situations where you have generic functions to work with. So let's have a look at that. So we've got some function h, which is a composite function f of g of x, and we're told a few key points. So we're told g of 3 is equal to 4. We're told g dash of 3 is equal to 6. And we're told f dash of 4 is equal to 8. And our goal is to find, so we want to find h dash of 3. That is an interesting question. I guess the first thing to ask here, h dash of anything, what does that actually mean notation-wise? We actually did an example of it in the previous question. What does h dash of 3 mean as far as mathematically speaking? Put it into context, what we did was y dash of 1 in this example. So h dash of 3 would therefore be something to the effect of, yeah, thanks Pia, derivative when we sub in 3. Nice. Specifically derivative of h when we sub in 3. So that gives us context on how to move forward now, because we know to find h dash of 3, we at least need h dash, which we don't have currently. We've just got this f of g of x nonsense. Tricky business here, because there is no real generic thing to have a look at as far as the table of derivatives. We don't know if it's a power function, an exponential, logarithm, circular function. We don't actually know what kind of function it is. But we do have an advantage, which is if we don't know what the function is, if I just had some generic function f of x, I know that derivative will always be called f dash of x. And that we can work with. So even if we don't know what the original one is, we know it's going to be called f dash no matter what. So this situation here that we have, this is a chain rule, because what we have is a composite function. We have some other function subbed into another function within a function. Whenever you have composite function, the chain rule applies. So with that in mind, how might we start off finding h dash, the derivative? I wonder if I have a pre-written version of what that looks like. Let's see. Nah, I've got them for specific functions, not quite for generic ones. That's okay. So the first step of the chain rules that we've always been doing is you take whatever's the inner and you do a substitution. In this case, it's a bit redundant to do a substitution. You're just renaming it from g to u, but let's just do it because it's what we're used to. U is equal to g of x. So you take whatever's inside the function and you replace it with a substitution. From there, you can rewrite the function. So now we have h of u is equal to f of u. That's about it. It was f of g of x, you replace the g of x with u. Now, from there, next step of the chain rule is finding the derivatives of each of these. As I said before, we don't actually know what these functions are, and so what we have to do is rely on just our notation. derivative of g is always going to be g dash. Derivative of, well, in this case, derivative of h dash u is going to get us to f dash u. From there, to complete the chain rule. Oh, yes, Sanjay?
Oh yeah, so if the equation was hx is equal to f of gx, right?
Yep.
And we're saying that gx is equal to u, then shouldn't you write hx is equal to f of u, not hu is equal to f of u? Why did we
H.
substitute u in h?
We did it before. We did it, well, I guess I didn't really mention what the variable is, but basically whenever you write a function, you got to write the name of the function, which in this case is h, and then the variable that it's a function of. So if there was no, like if this said x over here, this would also have to say x. It's more of a notation thing rather than like we're not necessarily like replacing the functions with u both. This is more so just saying, hey, this is now a function of u rather than of x anymore. Was that any clear?
No, not really.
Not particularly? Okay. So to clarify, I guess, what this previous example would have been, when we did our u over here, really, if you wanted to be super specific, you would call this u of x, because it's a function called u, and the variable in it is x. Is that clear so far?
Yeah.
Same thing over here. We've now rewritten our y without any x's in there anymore. So, like the full notation of this should have been called y of x previously, because it's y and the variables in it are x. So when we go ahead and do our rewritten version with u in it, there's no more x's in there. So we're just going to call this y of u instead of y of x anymore. How's that?
Okay.
It's pretty much just notation. It doesn't actually change how you handle things, but that's why it's been rewritten.
Okay.
So I could have just as easily said h and h dash. We didn't really need to specify the u in there. I just more so did it because, well, that is just a notation.
Oh, okay. All right.
Okay, so we have our two things there. All we're doing is doing our multiplication. So derivative, well, dy on dx is going to be the multiplication of those two things. So you're going to have g dash x and f dash u, but we also know that u is equal to g. So f dash g. Remember, that gives us our full derivative there. And this is what every chain rule looks like. You have some composite function, and you always just do derivative of whatever the substitution is out the front as a multiplication of your derived function. So what we've just done here is show that the chain rule for any function ever, any composite function, can be solved like this. But okay, that gives us that. But that's not quite what we're after. Probably shouldn't have called that dy on dx. That should have been called h dash of x. So that was the original name of the function, h. We don't want h dash of x though, we want h dash of 3. What might we do?
Sub in 3 everywhere you see x.
Sure thing. H dash of 3 is equal to g dash of 3, f dash of g of 3. Cool. It's not fully simplified yet though. What might we start doing to simplify what we have?
G dash 3, well, it says G dash 3 is like 6. So you could replace that with like 6.
Absolutely.
And then F dash, like inside the f dash function, it says g of 3, and we
Yep.
know that g of 3 is like 4, and then f dash of 4 was 8, so you can like just rewrite that whole thing as 8.
Absolutely. Yeah. And so just like that, even if you don't know the individual functions, as long as you know enough information about them, like regarding the points that we had here, for example, you can still go ahead and solve something like that. And so yeah, we have final answer, h dash of 3 is equal to 48. This actually came up not as a chain rule, but as a different kind of derivative technique called the product rule. This exact thing that we just did here, where we had to work purely with generic functions and just a few points, this was a multi-choice, I think, on the, not the most recent exam, but the one before that. But that's another type of derivative technique we'll look in the next group class. Well, the next time class 2 comes around, I think. Cool, I mean, that's that, really. There's another one in there that has our f, generic f functions in there. If we could do that, question 8, then question 6 shouldn't be too bad. So I'll move on, unless anyone wants me to have a look at that. We can sort of see if there's anything else interesting worth having a look at. So 9f is essentially just a redo of what we just did. We're still only looking at power functions here, even if those powers are fractional. In fact, you know, there are a few chain rules in here as well. So even if your powers are fractional, you're still doing your power down the front and reduce it by 1. So I make that explicit here as a sub point. If you have a fraction, whatever that fraction is goes down the front, and you reduce that fraction by 1. Otherwise, it's the same as what you've already done. The only thing you have to be able to do differently here is be able to convert your roots into fractions. So when you have this cube root of x squared plus 2x, it'd be better to rewrite it as power of a third, at least as far as like your actual understanding of it. Yeah, you could go from here straight to here, but at a certain point, you'd rather just make life easier for yourself and make the notation readable. Is everyone clear on how roots can be converted to fractional indices? If not, hop off mic, or hop on mic rather. Okay, so with that in mind, the rest of this shouldn't be too crazy. We'll do at least one of them. Let's see. Yeah, let's just jump straight to 4D. Why not? Almost used a pencil on my screen. That wouldn't have been nice at all. Okay, 4D. Got the cubed root of 4 minus 3x. And we want to just do derivative of this. Why isn't it focusing? Come on. There we go. Cool. So, first things first, we have this cube root here. What would be a good idea before doing the derivative?
Convert it to a power of 1/3.
Power of a third. Nice. Y is equal to 4 minus 3x all to the power of a third. Cool. What are we going to do here to now find this derivative?
Do you bring like 1/3 as a coefficient to the front and then make the power a negative 2/3?
That's certainly part of it. 4 minus 3x, negative 2/3. There is something that's missing from that.
Multiply it by -3.
Multiply by -3 is correct, yeah. Why are we doing multiply by -3?
Because that's the derivative of the u bit of it.
Yeah, correct. So what we've essentially just done here is the chain rule, but really, really fast. We didn't really explicitly do each of the steps. So this is still chain rule because you've got something other than x here. So you need to do, this is your u dash is going to be -3, which is why you've got to now multiply this whole thing by -3. So -3 at the front of that, which is going to give you negative bracket 4 minus 3x all to the power of -2/3. So we saw that here, where essentially if you have a composite function, you basically do derivative of whatever the function is. So that's what step 1 was when we put our power of a third at the front and then reduced it by 1. But you also need to multiply that by the derivative of the inner, which in this case our inner was 4 minus 3x, which I put a -3 at the front there. So that is what every chain rule looks like if you were to just use that that function or that expression of it. Clear enough there, or would you rather see it as the u dash y dash sort of situation? Cool. Question 5 is a unique one. What is going on there? I don't think it should be too crazy. Let's see how we can go. So, question 5. We want to prove that the derivative of this, so square root x squared plus minus a squared, prove that that is the same as x over square root x squared plus minus a squared. Fix that up just a touch. And while I fix, go away. There we go, that's better. Okay, so prove that derivative of left is this right hand side. What might we do?
Would you want to rewrite the square root as the power of 1/2?
Sounds good to me. Let's call it y, x squared plus minus a squared, all to the power of 1/2. Sounds good to me. What else? This bit here is actually kind of important. The fact that we're deriving with respect to x actually matters. So we treat x as the variable and a as the constant rather than the other way around.
If you're treating a as a constant, does that mean that you would get rid of it in the derivative?
Yeah. Even if it's a plus or a minus, a squared is still just some constant. Like if we pretended a was 3, then 9 is really not that much different. It's still just a constant. No kind of squaring will give it a variable. So for chain rule, we got something inside of something raised to a power. We could have something like u equals x squared plus minus a squared. Derivative of that with respect to x, 2 comes out the front, and you're essentially going to have a plus minus 0 because this is treated as a constant when you're deriving with respect to x. So u dash in that case is going to be 2x. Your y of u is now going to be u to the power of 1/2, and, well, y dash of u, 1/2 u to the power of -1/2. From there, multiply the two things together. Going to have 2x multiplied by 1/2, so just x. And then that's going to be multiplied by u to the power of -1/2. Now, this is what we have currently for our dy on dx. How do we make this look like that?
We convert to positive indices by bringing the u term down, but
So
also reverting back to its original form.
correct, yeah. So step 1 is positive index. Going to have u to the power of a half now. That is also the same as the square root of u. We knew that from before. And then final step in there, u is equal to x squared plus minus a squared. And so we're just going to do that. dy on dx is equal to x over square root x squared plus minus a squared, as required. That's about it there, really. Part B is a duplicate of that kind of question, and you can see the similarities between the two answers. If there's any questions about that, let me know. Otherwise, I'm going to have a look and see if 6 is... Yeah, 6 is interesting, because now you got a dy on dx that also has a y in it. I'll start writing out 6, and if anyone wants me to clarify anything before, let me know. Okay. Y is equal to x plus square root squared plus 1 all squared, and we want to prove dy on dx. So dy on dx is equal to 2y, and that's the weird bit here. You got to somehow get a y into your derivative. Square root x squared plus 1. All right, what gives? What are we doing? I'd say don't worry about the y that's in there necessarily right now. There will be a way to get it back in there. Let's start with our basics, which is, well, which is what? How do we start off every chain rule? We substitute, we take whatever's inside our brackets, and we replace it with a variable. U is equal to x plus square root x squared plus 1. Derivative of this is again yet another chain rule, so that's a bit nasty. One thing you might do here, rewrite your u, x plus x squared plus 1 to the power of a half, and now it's a bit more obvious that again you've got another chain rule situation going on. But okay, that's that bit. You've also got y of u is equal to u squared, because u is this whole thing. Y dash of u is nice and easy. It always is for the chain rule. At least that section of it anyway. Now from there, we need to figure out u dash. So part of this is pretty trivial, because derivative of x is always just 1. We've also got to do derivative of this, which is yet another chain rule. So by the time you get up to these questions, you shouldn't necessarily need to do as explicitly as what I'm doing, which is, okay, I see chain rule, I need to break it up into u dash, y dash, and then multiply together. By the time you get to this stage, doing it this way multiple times back to back actually ends up hurting you more than it helps. So for that, or to combat that, you identify that this is still a power function, so power comes at the front of a half. Brackets stay the same, gets reduced by 1. But then you go ahead and find the derivative of what's on the inner in there, which derivative of inner is 2x. So you multiply that whole thing by 2x. You could split this off into individual, like, I don't know, call them like v and v dashes. You could do that as well if you wanted to. At that point it gets a bit messy though, so being able to do these in line is pretty helpful. To fully simplify, the half and the 2 are going to cancel, giving you x bracket x squared plus 1 all to the power of negative a half. So we have our u dash, we have our y dash. More complicated than before, but we're still following the same steps. We've done our y dash, we've done our u dash, we now multiply these two things together. So, going to have 1 plus, yeah, let's make it a fraction. So instead of having the negative index, we'd have the square root on the bottom. And then all of this needs to be multiplied by 2 times u, where u is equal to that. So 2 times x plus square root x squared plus 1. Then from there, let's see, what would be doable here? Probably at this point, you'd get this as same denominator. That might be the next best bet to fully multiply these through. Because at the end of the day, we do want to get it to here, which is all over same denominator. So doing that in advance is probably a good idea. There's no real like right or wrong here, as long as you're doing things that are mathematically sound. The way you simplify this isn't as important. It's more so very heuristic based. Anyway, to get the same denominator, we're going to have square root of x squared plus 1 on top and bottom of the 1. And it's going to be a plus x, also square root x squared plus 1. And it's going to be multiplied by, well, the 2 we can put out the front here. And then x plus square root x plus 1. X plus 1. Okay. And what else could we do to start simplifying this? These are the same thing. So x and x squared plus 1 square rooted is the same thing here. I've just written the terms in a different order. X plus square root x squared plus 1, x plus square root of x squared plus 1. So when you multiply two things that are the same, that's the same thing as having the whole thing squared. And so what that ends up meaning is you're still going to have the 2 at the front here. Then the thing on top, square root x squared plus 1 plus x is going to be all squared over square root x squared plus 1. Still going to have that too. And now the fun bit here is we still need to make this look like this, 2y on the top instead of what we have. Now hopefully, how much of that's readable? Yeah. So we want it to look like this. Our denominator is fine so far, square root x squared plus 1. We've got the coefficient of 2 like we want. We could put it in the top, obviously, and we will. But how are we going to get a y in here? We currently got this. How are we going to get a y in there? One tip worth mentioning, there's only ever, in this entire working out, there's only one place where y is ever defined. It's up here. So this thing here, y is the same thing as x plus square root x squared plus 1 all squared. What you might notice is that that's exactly what we have here. X plus square root of x squared plus 1 all squared. These two things are the same, and so instead of writing all of at numerator, we just replace it with y. 2. You know, fine, we'll finish it off in red. Why not? 2y square root x squared plus 1. Monster question. Monster question. At least as far as the arithmetic required there. But not uncommon. Being able to do this in the final exam is expected by hand. Especially Like these chain rules that you're seeing here, where you have like linear raised to some power, they're not super uncommon. In fact, if you have a look at your actual formula sheet, you'll find that the formula sheet doesn't use the exact same table of derivatives that I have. It will actually simplify some of the chain rules for you. It'll have like an AX in all these spots, and it'll show you how the basic chain rule works. And one of those is how you handle linear to raised to a power. So being able to do that in line isn't the end of the world. You can just look at the sheet that you're given. But alright, that is end of class. If anyone has any quick questions, let me know. Otherwise, enjoy the rest of the day.